examples of calculations we can do using Coulomb's law. Obviously, things can get more complicated than just two charges exerting force on one another. Let's say, for example, we have three charges in a line. We have Q1 is 5.6 microcoulombs, positive. And let's say we have Q2, 3.1 microcoulombs, also positive. And then over here, Q3 is minus, 2.8 microcoulombs. Alright, let's say these two are 1.3 millimeters apart, and then these two are 2.1 millimeters apart. And let's say I want to find the force on charge 2. Right? This is applying our Coulomb's law and applying what we know about the direction of forces. So our force on 2 from 1 is going to be to the right because these two charges repel, and so Q2 is pushed to the right by Q1. And then these two charges will attract, and so the force on 2 from 3 will also be to the right. So both of these are going to be positive values. They're going to add together. And from there, we just plug in numbers. The force on 2 because of 1 is K. Well, actually, we can pull the K out front of everything if we want to. Force on 2 from 1 is Q1, Q2, which is 5.6 and 3.1. This will make things easier to punch into your calculator. You just do this, and they're both times 10 to the minus 6. So that becomes times 10 to the minus 12. And then that's over the distance between them squared, which is 1.3 millimeters. 1.3 times 10 to the minus third squared. That's F21. And then F23, we've got a K. Again, 3.1, 2.8 times 10 to the minus 12. That's a 12. Sorry, I wrote that small. I was running out of space. Over the distance between those is 2.1 millimeters. That's 2.1 times 10 to the third. 10 to the negative third, sorry, squared. Actually, for this segment of the course, I would recommend, I don't know if I did this in this calculator yet. Nope. Take your 8.99 times 10 to the minus times 10 to the ninth and store that as K. And then when you're doing your calculations, you can just type K in instead of writing out the whole number. Anyway, so then if we punch that into our calculator, we get 110,041.5854 newtons. That's huge. So you can see that the forces between electrical charges are really big. Yeah. Now things can get even more complicated. Actually, before we do that, let's forget about Q3 for a minute here. Let's now say Q3 is not there. We just have Q1, 5.6 microcoulombs, and we have Q2, 3.1 microcoulombs, and they're 1.3 millimeters apart. Now I have my new question is where could we place a charge so that there is zero net force on it. This is another way we could apply Coulomb's law. So let's first think about where this could happen. I should say a positive charge. Where could we place a positive charge so that there is zero net force on it? Let's think about the direction of our forces. Say we put a positive charge out here. Okay. The force between these two is repulsive, so that would push this charge to the left. The force between these two is repulsive, so that would also push this charge to the left. So we couldn't get a zero net force if it was out here. If it's in between the two of them, the force between these two is repulsive, so that would be a force to the right. The force between these two is repulsive, so that would be to the left. So that could work. Out here, the force between these two is repulsive, so it would push the charge to the right. The force between these two is repulsive, so it would push the charge to the right. So we can only get a zero net force in the middle there. And so we can set up an equation very similar to what I did right here, except we want our net force to be 0, and that's equal to K times, well, we don't know what this is, but we can just call it Q, and so we have Q times 5.6 microcoulombs over, we don't know what distance this is, call it X over X squared. Then the force from Q2 is going to be to the left, so we say minus this unknown charge times 3.1 microcoulombs over, well, if this is X, then this distance is going to be 1.3 minus X squared. And since we're solving for X, there's no problem with just using 1.3. Just remember that when we get a value for X, then it'll be in millimeters and not in meters. So this is a little bit complicated, but it's just an exercise in algebra. We can get rid of the K because it doesn't matter. We can get rid of this charge because it doesn't matter. And we're left with, if we move stuff around a little bit, we've got 5.6 times 10 to the minus 6 over X squared equals 3.1 times 10 to the minus 6 over 1.3 minus X squared. We can get rid of the 10 to the minus 6, and then cross multiply. 5.6, 1.3 minus X squared equals 3.1 X squared. Move it over. I guess we could distribute, but at this point, I would just go ahead and punch it into your calculator. Maybe actually you might have wanted to punch it in your, you probably have just punched it into your calculator right there, and determined where the 0 is. Alright, now this is a quadratic, so there are 2 zeros. So we go calc 0, find this one, and this gives us 0.745. And let's calculate the other 0. And this is 5.078. Okay, so now there are two different solutions given here. But let's go back to our original situation. We wrote our equation based on the assumption that this charge is going to be in between the two of them. Now, if X is 5.078, this charge would not be between the two of them. It would be somewhere over here. But this equation isn't valid for somewhere over here, because for somewhere over here, both of these would have been positive. So this one turns out it's not a solution. Actually, this is a solution for, turns out this is a solution for what would happen if, or where you could put a charge to get 0 net force if this was actually a negative charge, because then these SIGN signs would be valid for a position out here. So this 0.745 millimeters is the value of X. That's the position where we could place the charge to have 0 net force.